In this video, we talk at length about the concept of conjugate acids and bases. Alright, so we have said that in acid-base chemistry, when you have an acid dissociation, that results in a proton and the conjugate base of the acid. And when you have a base reaction, you will have a generation of hydroxide and the conjugate acid of the base. Alright, so we're going to talk a little more about those conjugate acids and bases. Right, so let's think about an acid-base reaction between a strong base and a strong acid. Okay, so we're going to take hydrochloric acid in aqueous solution, and then we're going to add sodium hydroxide, also in aqueous solution. And the resulting products here, acid-base generates a salt and water. Okay, you will have the salt, which is sodium chloride, and then water. Now, something interesting that we can do here is examine what happens to the salt and what will be the pH of the resulting reaction. So if we assume a stoichiometric reaction between hydrochloric acid and sodium hydroxide, there will not be any acid or base left over, and the only thing that you have is sodium chloride and water. Sodium chloride, of course, is a strong electrolyte, and when you put it in solution, it really is fully dissociated into sodium plus and chloride. Because these ions don't have any acid-base properties, then the resulting solution will be neutral. Okay, so when you mix a strong acid and a strong base, then you generate, if the reaction is stoichiometric, then you will generate a neutral solution. Let's try to do the same thing now, but mixing a weak acid with a strong base. Okay, so we can take acetic acid, which is a common weak acid, and then we're going to mix it with a strong base, sodium hydroxide, and of course this generates a salt, which will be sodium acetate, and then water. Now we do the same thing, we take a look at the salt and see if the resulting solution will have any pH or not. Well, it turns out that salt, sodium acetate, dissociates into sodium and acetate ions. But the interesting thing here is that these acetate ions have acid-base properties. Notice that the acetate ion is the conjugate base of a weak acid. Okay, and that confers it some interesting acid-base properties, right? So when we actually put this in water, what will happen is that, well, because this is a base, then you can generate here acetic acid, and then the other product will be hydroxide. So naturally, a consequence of having this conjugate base in solution is that you generate hydroxide, and that makes the solution basic. Okay, so even if you mix stoichiometric amounts of acetic acid and a strong base, okay, because you're generating a conjugate base, which is rather strong, then the resulting solution will be basic. Okay, and that is very different when you have a mixture of a strong acid with a strong base. So we start to see how the presence of conjugate acids and conjugate bases that are strong will affect the pH of an acid-base reaction. Let's now try to do a similar problem here, but mixing a weak base with a strong acid. Okay, so our strong acid is going to be hydrochloric acid, and then we're going to mix it with a weak base, which is going to be ammonia. Alright, so the reaction will generate ammonium chloride, which of course in water dissociates to ammonium ions and chloride ions. Now, these ammonium ions are the conjugate acid of a weak base, which is ammonia. Okay, so they will have acid-base properties as well. When we put these ammonium ions in solution, then you actually have an acid-base equilibrium in which you generate ammonia and then protons. right? So because this is a conjugate acid of the base, you're going to have this equilibrium, and notice that there's generation of protons, so this will generate an acidic solution. All right, which is in opposition to what happens when you mix a weak acid with a strong base, and it's also different from when you mix two strong acids and bases. All right, so we can kind of start to establish a relationship between weak acids and bases and their conjugate pairs by writing this type of table that is going to, again, make the summary of everything that we have seen until now in this video. Okay, so we're going to take here all of the acids and all of the bases, and we're going to be looking at the acid-base properties. Okay, so let's write here a table of acids that we had. Notice that we started with HCl. We've also looked at acetic acid. And then there is a third acid, which is water, which can act as an acid as well. So the conjugate base of these acids, in this case, this will be chloride. In this case, you will have acetate, and then the conjugate base of water will be hydroxide. And there's a very important relationship between the strengths of the acids and their conjugate bases. Notice that hydrochloric acid is a strong acid. And what that means is that the conjugate base will be weak. And that's why chloride, when you put chloride ions in solution, there's no acid-base properties, right? The solution will be neutral. However, if you do the same with a weak acid, like acetic acid, right, you generate acetate, but those acetate ions are strong conjugate base, right? So what will happen is that, well, if you put that in water, acetate ions in water, then because they're a base, strong base, they will accept a proton from water and generate hydroxide, making the solution basic. And water, when it behaves as an acid, is also a very weak acid, right? We know that the dissociation constant would be Kw, that is 10 to the minus 14. And hydroxide then is a very strong base. It's actually the textbook base hydroxide, right? So again, this is a universal relationship. When you have a strong acid, you generate a weak conjugate base. When you have a weak acid, you generate a strong conjugate base. The same thing can be said for bases, and we're going to write here the list. Okay, so for bases, in the problem we had sodium hydroxide with it, which is a strong base. Then we also had ammonia, which is a weak base. And water can also act as a base. Okay, notice that water can act both as an acid and as a base. It's an amphoteric substance. And then we can write what the conjugate acids of this species would be. Right. Notice that in this case, the conjugate acid will be sodium ions, and that will be a very weak acid, and it does not exhibit any type of significant acid-base properties. Any solution of sodium plus will actually be neutral. Okay? Then the conjugate acid of ammonia is ammonium ions, and that is a strong acid, which when you have ammonium ions in solution, that solution would be acidic. And finally, when water behaves as a weak base, it accepts, it will generate protons, and that will make the solution acidic as well. Okay, so notice that again, there is a relationship between the strength of a base and the strength of a conjugate acid. A weak base generates a strong conjugate acid, and a strong base generates a weak conjugate acid. Okay? All right, so to wrap up this video then, we're actually going to then redefine a regular weak acid dissociation reaction, and then rephrase it in terms of the strengths of the conjugate pair at play. Okay, so let's look again at the acetic acid dissociation. Okay, in solution, aqueous solution, you generate protons, and you generate acetate. All right, so we know that the K sub A for this process is very low, 10 to the minus 5. Okay? And we're going to try to justify this low value of the equilibrium constant by looking at the strength of the conjugate pair at play. Okay, and we know that this is a weak acid, okay, and we know that this is a strong conjugate base, right? So the idea is that, well, there's more affinity because this is a strong base. There's a lot of affinity for the protons, and what that means is that the equilibrium is going to be displaced to the left. And that actually can be exemplified because your case of A is very, very low. That means that at equilibrium you have a lot of conjugate acid and very little conjugate base with protons. Again, so notice that how this concept of complementary strengths of an acid or a base and its conjugate pair is able to satisfactorily explain a lot of this equilibrium that we have in acid-base solutions.